Hello everybody and welcome to today's WTG webinar session. My name is Louise and I'll be moderating today's event. Our topic today is Modern Catalysis, Academic Discovery to Industrial Application, and will be presented by Professor Stephen Buchwald, Dr. Spencer D. Dreher and Dr. Sarah L.J. Treese. So let me just introduce our speakers. Professor Stephen Buchwald currently serves as Camille Dreyfus Professor of Chemistry at Massachusetts Institute of Technology. In addition to this, he also works as a consultant to a number of companies and is an associate editor of Advanced Synthesis and Catalysis. Dr. Spencer D. Dreher is currently the principal scientist of process chemistry at Merck & Co. Spencer specializes in high throughput chemistry and applied catalysis for drug discovery and development. And our final speaker, Dr. Sarah L.J. Treese, recently brought her catalysis and organic chemistry expertise to Sigma Aldrich and currently manages the Aldrich Catalysis portfolio globally. Previously, Sarah's worked at Merck & Co., where she served as a senior scientist in medicinal chemistry and led an extended interdepartmental catalytic screening center. This leaves me nothing more to say but to welcome today's presenter. Steve, you're now live.
Give sort of a brief introduction and then a little bit of an overview of chemistry involving the use of palladium cross-coupling primarily with biaryl phosphine ligands that were developed at MIT and have been commercialized throughout the world, and that Aldrich has a major portfolio of, and also the pre-catalysts that are based upon these ligands and other ligands, again, that are also widely commercial. Okay, so the first part of the talk is going to deal with not only the ligands, but also with carbon-nitrogen bond-forming reactions. And this really came out of the seminal work of Kosugi and Megita in 1983, who used tin amides for the couplings. There have been many others who have, of course, made, in addition to my group, who have made very important contributions. Certainly John Hartwig's the most notable, but also some others who are less famous. There's a group at Toso who invented the use of tritibutylphosphine as a ligand for cross-coupling reactions, led by Koya Nishiyama Yamamoto, and in particular I'd like to call out Anil Guram, my former postdoctoral co-worker, who was the co-inventor of what we did in CN coupling in my lab. So the reaction is essentially analogous to carbon-carbon cross-coupling that won the Nobel Prize in 2010. And just for those of you who are interested in the details, there's a recent, not so recent review now, but the most recent review, which is basically a guide to and a guide to troubleshooting as well, which was published in Chemical Science in 2011. Right now we're in the process, one of my coworkers and I are in the process of putting together a Chem Reviews article to update the literature in the last 8 or 9 years, for the last 8 or 9 years. Okay, so the catalytic cycle for CN coupling, what's amazing about it is sort of the broad overview has not changed since the original postulate, and in fact looks very similar to what would have seen in the early 1980s in a textbook like a Coleman and Hegedus for carbon-carbon cross-couplings. There are, of course, a few differences. One of the major changes is the relative importance and difficulty of the different steps has changed. So as with other cross-couplings, one needs to get to palladium 0. So you start with either a palladium 0 or palladium 2 pre-catalyst, and usually with a ligand. You do an oxidative addition with an aryl halide or pseudo-halide. In the early days of palladium chemistry, that was rate limiting, and that was why people were always told to use aryl iodides. I would say now Only use aryl iodides if you have to. Aryl iodides are often, and particularly with palladium catalyzed CN coupling, the most difficult substrates between chlorides, bromides, and triflates. Once you're at the palladium 2 aryl X, that's somewhat Lewis acidic. It can bind the amine. That tremendously acidifies the hydrogen of the bound amine. Deprotonation can occur. You can do this either with a strong base. Our favorite is sodium T-butoxide or lithium hexamethyl disilazide. In that case, that deprotonation is very rapid to form the palladium aryl amido complex. In certain cases, the combination of the amine nucleophile plus the base causes problems with functional group compatibility. And so then one has to resort to the use of a weaker base, usually potassium phosphate, cesium carbonate, or potassium carbonate. In those cases, the reactions are invariably slower, and the reactions require more catalyst. Once you're at this palladium aryl amido, reductive elimination forms the CN bond and regenerates palladium 0, your palladium 0 species. Now, when people oftentimes ask me what is the most difficult part of the catalytic cycle, I usually try to reframe the question as, what is the reason that reactions don't work the most when you do palladium catalyzed couplings? And in fact, oftentimes it's that one never actually gets to the active palladium catalyst. And that's why we have developed a series of palladium pre-catalysts to overcome this issue. So at least one knows that you've got the active catalyst going, and if the reaction doesn't work, it's some other culprit that's causing the problem. So we've focused a lot of effort in developing new ligands. We have a series of electron-rich bulky monophosphines. These are all prepared in either a one-step or two-step synthesis. This was a route that was invented by Joe Fox, now a professor at the University of Delaware. 20 to 25 ligands are commercially available, both from catalog companies such as Aldrich and Strem, but also there are 8 companies with licenses worldwide to manufacture. And in fact, if anybody uses ligands that buy from one of these 8 companies, including Aldrich, then there are no IP restrictions, there are no royalties due, and there are no licenses that one has to get from MIT. All the ligands are crystalline air-stable solids for extended periods of time, years. They have considerable stability in solution. In the absence of palladium, the presence of palladium, you'll get oxidation. We've probably made 1,000 different structural variations. The reactions have been run on, the amination reactions have been run on at least a 2,500 liter scale with these ligands, and we estimate, 1 to 2 metric tons produced and sold legally worldwide in terms of things. Okay, so there's a great variation in terms of the ligands, and that allows for different transformations to be catalyzed from this same family. So here's, on this slide shows sort of a 50 kilograms of one of the ligands from Aldrich. This is provided by Rob Todd. And this is T-butyl brettphos. This is a ligand that we originally thought would be the hardest ligand to make, but now it's one of the ones that's made on the largest scale. So the possibility of making hundreds and hundreds of kilos. So this 50 kilos is a single batch of T-butyl brettphos. Now we know when we started, we didn't understand all the features, and there was certainly a lot of serendipity that went into coming up with these ligands. And we now understand that what we need is to have bulky groups on the phosphorus, either cyclohexyl, that gives us the greatest turnover number, but in cases where reductive elimination is more challenging, particularly for CO or CF bond formation, we go to larger groups such as T-butyl or more preferably now adamantyl. The bottom ring stems from triisopropyl benzene, which is a gasoline additive, It turns out that this bottom ring coordinates to the palladium during the course of the reaction, which is very important and helps to protect the overall bulk, helps to protect the ligand and keep it from going to multiple ligands binding to the palladium. And then finally, the R group on the upper ring helps to orient things, and that leads to the catalyst systems with the highest turnover number. So when we think about how we describe ligands, we've got both steric and electronic effects. The steric effects we think are predominate here, and we go to ligands such as S-phos and X-phos, the cone angle, the Tolman cone angle, become very, very large. And that's only important because what it does is it decreases the coordination number of the ligand to the palladium, and we get more and more access to the L1 palladium. This is important because all of the fundamental steps, oxidative addition, transmetallation, and reductive elimination, have been shown to be favorable for L1 palladium complexes over homologous L2 palladium complexes. Okay, and so what we have here, people would say, well, what happens when you use a very large ligand? Don't you hinder things? But in fact, one large ligand is much smaller than two medium-sized ligands. You can see sort of a space-filling model of what X-phos, one of our ligands with palladium, looks like. And you can see that there's a very large ligand, but there's a lot of open space. What the large ligand does is prevents bimolecular interactions, which cause a lot of the undesired side reactions, such as homocoupling, and allows reduction to occur. Those are minimized to a great extent using these systems. You also can see from the depiction on the lower left that there is a palladium ipsocarbon interaction that shows up in all of our X-ray crystal structures and also the DFT calculations. And we think that that is one reason for the stability of the active catalyst. Okay, so our group has developed a lot of ligands. And in fact, a number of the ligands are named after the cats in my household. And the most famous of these is Rufos, which is named after Rufus, who is shown on the right. And this is a recent group T-shirt designed by Dr. Christine Nguyen. Okay, so and pays homage to all of the cats and how they've had a direct impact in giving advice to us. All right, so we've got the ligands. Why do we need the pre-catalysts? And a lot of this comes about, I'm very fortunate to have really good interaction with people at a variety of companies, both consulting and just informally. And I could essentially integrate the comments that I got from people, and along with work that we were doing at MIT, to understand why reactions that looked like they should work weren't working. And from that, it became very apparent that a lot of the time we weren't getting active catalysts into the catalytic cycle. And so we've shown that pre-catalysts have advantages in a lot of cases. Even in cases where you can get it into the active cycle, this gets it into the active cycle more efficiently, faster, oftentimes at lower temperatures, and using milder conditions, weaker bases. All right, so as I said, one of the biggest challenges is how you get into palladium zero, the active species. Of course, one can say you can buy palladium zero complexes. The most useful for us has been PD2-DBA3, with DBA being dibenzylidine acetone. And that DBA is a strong ligand, so we wanted to have a system that worked better. You can use palladium acetate. That can be reduced in situ sometimes, however, not well with, for example, anilines and amides. So Mark Bisco, when he was a postdoc in my group, and now he's at City College, was able to develop a system which, based on mechanistic thinking, that has the intermediates in the catalytic cycle, liganded palladium with the oxidative addition complex, followed by binding of the amine. We made that independently and showed that that very rapidly was converted to palladium zero. And that gave us the ability to very carefully control the ligand to palladium ratio from 1 to 1 on up. And this activation we showed was done in about 4 minutes at room temperature, although with weak bases required 80 degrees. And here's just a brief comparison of a reaction with and without pre-catalyst, and you can see the bottom green line, I won't go into detail here, is the reaction with reducing agent, and then we tried a bunch of different things, adding amines, adding phenylboronic acid, and that confirmed that we needed to have something that would allow us to do the reaction more efficiently. This is when we compared those with the pre-catalyst, and just to cut to the quick, the light blue line, the top line, shows that the reaction is much faster than either using DBA, palladium acetate, boronic acid, or Al-palladium chloride dimer. Okay, so we have evolved the catalysts. We started with G1 and G2. So Bisco pre-catalysts were G1. The Yang pre-catalysts were G2. You can see some of the pluses and minuses of these different pre-catalysts. Because of time, I'm not going to go into the details. I'm going to speak more about what we prefer now. So we've got the G3 pre-catalysts invented by Nick Bruno. These are really great. They can be made on large scale. They're stable even in solution. We can make them and use them for a wide variety of ligands, both our ligands and other people's ligands. It's actually, the ligands are so easy to make that this is the G2, is an undergraduate laboratory experiment at Harvard. Okay, and now we've got the G4, and that is where we put primarily a methyl group, so R is methyl, onto the ligand, and that is for a very small number of cases, one has a situation where the carbazole that's formed in the generation of the active catalyst can cause a problem, and so this obviates that issue. And this is particularly going to be important in systems where there's difficult binding of the amine substrate to the palladium. All right, so that's the timeline for that, and there was a review article that was published in ACS Catalysis by a French group that's highlighted here. Okay, so palladium catalysis have had an impact in a lot of areas, certainly pharmaceutical, but a lot of other areas, maybe less well known, OLEDs, probes, semiconductors, polymers, certainly agrochemicals as well. Our ligands have been applied in a number of instances. Again, without going over the details, we really like it when our compounds are utilized in real-life situations with polyfunctionalized systems. And that's really a focus on what we try to do, is to find things that don't work and understand why they don't work from a mechanistic perspective and try to solve these problems so other people can use them. And so now we've got a few examples. This is work from Neumeier, where he showed that how the Brett-Foss G3 pre-catalyst allowed a reaction to go in virtually quantitative yield that using traditional methods goes in about 10% yield. There are a number of other applications. I don't have time to describe these in detail, just leave them for you to see as examples. One case that can be challenging is when you have poorer nucleophiles such as sulfonamides. This is a case by workers at AbbVie where they used T-butyl Brett-Foss to make compounds related to their hepatitis C program. Okay, one can of course run these reactions intramolecularly. These have been used in terms of making natural products by chemists such as Phil Barron, one of the masters in that area. And here are another couple of examples of the applications of these ligands in total synthesis. Okay, in addition to this, there have been some really cool applications in material science. Here's some work from Uwe Bunz, who has made persistent diazaheptacine derivatives using the Rufus pre-catalyst systems. Here are some caged compounds that Ito has prepared using Rufus along with DBA complex. And here are some even more complicated systems from Lee and Schneebeli that came out this year, or last year in Angewandte Chemie. Now, another place where we see a very good application is with Suzuki Miura couplings. And one place is with unstable aryl boronic acids. This 2,6-difluoro phenylboronic acid was very problematic. It turns out that the difficulty was it has very, very short half-time at room temperature, and so the typical idea that one tries a reaction at 80 degrees and if it doesn't work goes to a microwave was actually going in the wrong direction. One had to cool the reactions down to room temperature. We found at room temperature these reactions were very simple if we used oxidative addition complexes, particularly using, we started with S-phos, moved on to X-phos, that gave us the best results, and then we found using the type 2 pre-catalysts we could run these reactions at room temperature, and at room temperature we could get very good substrate scope in the reactions. Okay, and here are a few other examples. There were some cases that didn't work. We have solved that. We can do that chemistry as Negishi couplings. I don't have time to talk about that. And the problem really is in these cases not the rate of transmetallation, which was a question before, but the rate of protodeboronation. You can see for the 2,6 system and THF at room temperature in the presence of base, it's got a half-life of 28 minutes. For the trifluoro, it's got a half-life of 2 minutes, and of course you have essentially no chance under those conditions. Okay, the same thing goes for heteroaryl boronic acids. Oftentimes if you run these reactions at 80 or 90 degrees or above, the reactions work very poorly. If you run the reactions at room temperature or 40 degrees, the reactions work quite well. And this has been applied in a number of cases, including on large scale by Merck. I think they did this with 29 kilos of the, on 28 kilo scale to make the product shown. Okay, there have been some extremely nice applications by Marty Burke in a number of different publications, one of which is this Nature Chemistry article. He's used these applications both in his machine chemistry and also in his synthesis. And again, many cases I've heard of both personally and in the literature where chemistry which didn't work well for the ligands by themselves with palladium acetate, when one went to the pre-catalysts, all of a sudden the chemistry worked. Okay, there have been some, again, cool examples in materials science, and I'll just leave you, this was the last one I'll talk about, where they've used the functionalization of diamond and they got a 98% improved coverage using our ligands as compared to using tetrakis. But anyway, thank you all for your attention.
So just by way of introduction, you know, looking at the drug discovery paradigm, we're preparing design molecules to test biological hypotheses, and then we have process chemistry, wherein we're trying to make the important molecules that we find in that process perfectly in regards to the, you know, their elegance, their minimizing cost, and decreasing the environmental impact. My job at Merck is in the Enabling Technologies group, and within that group, the Catalysis and Automation group, and we're focused on trying to help anyone throughout this process make difficult molecules. So I wanted to just start by underlining the idea that I think that we are in an amazing age of academic excellence. There's just endless beautiful new papers coming out all the time, wherein, you know, we're really taking fundamental problems and either reducing them to practice in a new way or finding new ways to activate chemistry, you know, for example, photoredox catalysis, recent work in the Buchwald group wherein they are starting to functionalize macromolecules and then even using enzymes. At the same time, though, we understand in our own labs that the kinds of chemistry that's actually used to make new drug molecules is largely textbook chemistry, the stuff we learned in graduate school 25 years ago. Most of this new innovative work is not making its way into synthesis. And if you look at what sort of modern catalysis people actually do, it's largely Suzuki reactions and CN couplings. Everything else just kind of falls off after that. And you know, there's a lot of people looking at this, and a very recent paper just came out from Brown and Bostrom, which I would encourage you to read. It doesn't have a page number yet, but look in JMedChem, where, you know, where have all the new reactions gone? So we're not the only ones seeing this. The question is, why is this happening? And just to give you one sort of perspective on it, if you look at a typical molecule that we're trying to make, such as Januvia, you can see that these molecules have a large number of nitrogens. The carbon to nitrogen ratio in this molecule is about 3 to 1. If you actually, again, this is from our electronic notebooks, if you actually chart chemistry performance as a function of nitrogenation, textbook chemistry actually ends up performing reasonably well as you add more nitrogens on, whereas catalysis, the numbers drop out the bottom as you add more and more nitrogens on. And so these same nitrogens that are important as communication points with biology are also potent chemistry killers. So at Merck, let me describe the catalysis process that we use to try to solve problems. So one thing that we've done is we try to equalize the communication around what to do with catalysis. So we have a catalysis selection guide that we send out to all Merck chemists, and we scour the literature, making sure we understand what we think are the best conditions. Within our electronic notebooks, actually even have pre-designed experimental molecule in, and it sort of reduces the potential error involved. Okay. And so we also are recommending, inertia techniques and things like that in order to really give ourselves the best chance of actually making the molecule with the literature conditions. The problem is, though, that we're trying to make molecules such as those in the middle of this. These are the starting materials for synthesis, where we're trying to react at these halides. And we did a recent study showing that the types of examples that are demonstrated in the literature are certainly growing in complexity, but certainly for almost any new synthetic method, the scope that's demonstrated is very simple. And so all of these sort of physical chemical properties that are important in actually interacting with biology, we just don't see them in the literature examples. And so this is just one example of things like the size, the solubility, the polar surface area, the hydrogen bond donors and acceptors, the rotatable bonds. It all adds up to, we're trying to do things that simply haven't been demonstrated before or not demonstrated systematically. And another recent paper that just came out from our group sort of looks at this in a more visual format. If you array known drugs based on several of their physical properties, we call it the principal component analysis, and you compare that to compounds in the literature. The compounds in the literature on the right in blue and red, and the drugs are in gray. You can see pretty clearly that these are the substrates that have actually been tried in methods papers in the literature, and by these metrics, they tend to be small. They tend to have far less hydrogen bond acceptors than drug molecules. They tend to be more greasy, and they tend to be highly aromatic and flat. And so what this means at the end of the day, if you see the big red circle, all of this space is the actual space we're trying to make molecules in, complex new molecules, and we've almost not studied what to do there. So how are we going to solve this problem? At Merck, we've decided that we're going to take a course of high-throughput experimentation chemistry. So in traditional experimentation, you are going to read the literature. You're going to look for something that looks similar to what you're trying to do, and you're going to try the best set of conditions. And again, we've made every effort to make sure people know what those best conditions are. At Merck, we've really pushed the envelope on trying to use high-throughput experimentation chemistry as an alternative. Now what we're doing is we're taking the same literature and we're trying to run all of it at the same time with permutations on the conditions that are there. And so if you have different catalysts, different bases, different solvents, these are all things that are precedented to work in one system or another, but we're putting them all together. And then we're also combining in our own sort of internal knowledge to try to solve these problems. So using this approach, this bar graph here is getting quite old now, but what it shows you here is if you take any of these types of reactions and you run them with the literature conditions and they don't work. So there's some certain percentage of times that they do work. If they don't work, we can take a high-throughput experimentation chemistry approach and find workable synthetic solutions this percentage of the time. So Suzuki 85% of the time borylation, 80%, et cetera, et cetera. And I think most excitingly is that, if you apply the same sort of approach to any of the other types of chemistries that are out there, including photoredox catalysis, iridium catalyzed borylations, just, organocatalysis, anything like that you would like to explore, we can actually find solutions to problems within this net that we're forming. Okay, so what we found pretty quickly is that we can do just about any type of chemistry that we need to in this regard. And so in the last probably 5 years, we've embraced sort of this idea that we need to be communicating what we're finding here. We're certainly not the only ones doing it, but there are a lot of people doing it with the academic community. And we have interactions going, either collaborative interactions or consulting type interactions going with everybody on this slide. And I wanted to particularly highlight the University of Pennsylvania, where we've worked with Professors Molander, Kozlowski, and Walsh to really build out this idea of high-throughput experimentation chemistry. But you can look in the literature and you'll find dozens of papers now from these groups using high-throughput experimentation. So in the first sort of 5 years of high-throughput experimentation at Merck, we saw pretty clearly that we could impact process chemistry and also sort of academic reaction discovery using this sort of what we call 1980s biology approach to chemistry. However, if you really want to impact medicinal chemistry, you really have to kind of think differently. And in medchem, materials can be precious and timelines are very tight. So, you have to be able to solve problems quickly and with little amounts of material. And so this, one of the ways to actually conserve material is to consider miniaturization, and this is something we put a lot of energy into. This is an example of our validation kind of work that we do, wherein this is a Suzuki reaction that we know is sensitive to stirring and heat sensitive as well. We ran 24 different sets of reactions in 8 ml vials, and you can see how they're rank ordered in the dark blue in terms of the conditions and the yield. We then repeated that in 1 ml vials, and then in what we call microvials in increasingly smaller scale, and you can see largely that the data that we get is scales down very well. So by the opposite, if you find something on 1 milligram scale in a small microvial, it should scale up as well. Just as important, though, is not only running reactions in smaller scale, but it's actually making better decisions as we go. And so one of the things that we tried to study early on was, can we take our 96 reaction plates that we pretty much routinely did at the beginning and boil it down into smaller reaction arrays? And so this is where we kind of came up with the idea that we called kits for a long time at Merck, taking what we learned in a sort of informatics sort of way from looking at 96 well screens and running 24 reactions at a time instead of 96. So we're conserving material that way. And what we found is that we were actually pretty good at running, translating the hits from the larger arrays to the smaller arrays. And so, ideally, you want to run all of as few experiments as you can, right, to solve the problem. And so we want to be pushing towards less and less reactions. And this is largely an informatics problem, I believe. And obviously, as Steve would say, understanding, right? So, what is it that is special about these types of conditions that work versus those that don't work? Okay, so very important to this whole initiative is the pre-catalysts that Steve described. Early days, when we first had the idea of making these kits, the idea here is that we want to pre-dose into vials the reagents, catalysts, et cetera, that will be needed to solve a problem, and that a chemist in any lab could actually take this kit and run it anywhere. The problem is that we started this initiative just before sort of pre-catalysts were published at all. And early days, we were trying to mix palladium acetate, ligand, and base in vials and ship that out. And we found that we could actually get good chemistry oftentimes to work, but that these kits were unstable. right? They would start to decompose. We had to keep them cold until they're ready to use. So at Merck, Matt Tudge led the effort to kind of figure out how to use pre-catalysts to accomplish this same goal. And so, we have a lot of pre-catalysts now available, and I can say, we've got the G2 and G3 pre-catalysts here, and I would say that we've probably found valuable chemistry results with everything that's on this page. So ligand diversity, catalyst diversity is very important to solving problems. I will say, though, with 100% certainty that the Buchwald portfolio is the best place to start. There's no question about that. It's extremely high quality stuff. So show you what sort of kit screening looks like at Merck. So here's two Suzuki reactions side by side. And on the top, you see you kind of have a relatively vanilla-looking boronic acid. On the bottom, you have a nitrogen-containing boronic acid. Pretty simple change. What we're going to do is we're going to run 6 different of these pre-catalysts and 4 different solvents against this problem. And what you'll see here is you run the top Suzuki with the kit, and everything works. Okay, so this just shows you that every set of conditions on this kit is reactive. Okay. For a relatively basic system. You add 1 nitrogen into the system, and everything drops out except for 1 hit. I will say that this is our experience more often than it's not. When we run a kit, again, these are usually the problems that have been identified as being difficult. They didn't work with the best set of conditions. We find very few hits in a small screen like this. Nonetheless, we pretty reproducibly do find hits. So, and I can also say with this result in hand, it's very difficult to rationalize why this particular catalyst and this particular solvent was best. And obviously, if we're working in drug discovery, that's not what we're focused on. So, this does allow you to move quickly and solve problems. So, I think that we are living in a world in chemistry where people are looking for the magic bullet to solve problems. And, I think this paper came out 3 or 4 years ago from the Buchwald lab where he described the XPhos G2 catalyst as being particularly good for sensitive boronates. And somehow we got this notion around Merck that this was the magic bullet for Suzuki's. Again, we put it in our selection guide and we said, okay, go with this. This is going to solve all your problems. Our success rate went up, no question. It's a better catalyst system than had been reported before, but what we find over time is that this sort of kits-based approach, wherein we are running an array of catalysts, an array of bases or solvents, this kind of approach, what we see is that if you run this system in that small array, it hits a certain number of times, but it's pretty well spread out in this array. The number of, so if you take 31 kits that we ran in one sequence at Merck a few years ago, 14 different catalyst-solvent combinations gave the best conditions. And again, this is something we see over and over again. And so what is the magic, the bullet? The real magic bullet is running a small, intelligent sort of array of conditions to try to solve a problem. And you're going to work your way through solving problems quickly. And I would say this kind of approach is going to be useful for any type of synthetic problem you're going to try. I don't think there's any type of chemistry that's come along that we haven't been able to figure out how to do this for. Okay, so this is bringing it all together. This is a slide that Steve showed a few minutes ago, this chemistry, and I just kind of wanted to show this at the end because it brings this whole talk together. So interestingly, this MK8876 development compound, we were trying to do a borylation reaction, and if you use bis-pinnacle diboronate, you get a lot of the dehalogenation impurity. It just so happened at the time, Sarah Trice was working on her PhD and came up with conditions as to how to do this boronic acid cross-coupling, and it worked beautifully. But it required the use of a pre-catalyst from the sort of G2 variety. We then went and did a Suzuki, as Steve described, on 29 kilos. I will just finally add here that both of these results were found early on with kits. Okay, so We had a boylation kit, we had a Suzuki kit, and we found the results for this. Okay, so as in everything in industry, this is an effort of a large group of people, and so you know, I just wanted to acknowledge that this is what I presented today was from the work of a lot of people in the Catalysis and Automation group, and also work with our external collaborators. So, thank you.
All right, great. So I just want to say it's truly an honor to present alongside two of the visionaries in modern catalysis. Most of us with any pharma experience are intimately aware of the innovative work from Professor Buchwald's lab, and we're all grateful to the work of Steve and his brilliant graduate students, both past and present. Also, from my perspective, Spencer and his team at Merck & Co. are rapidly changing the drug discovery game. They perform practical, enabling research, and as evinced from some very recent publications, they're willing to share this knowledge with the rest of us. And for that generosity, we in the chemistry community should be very thankful. So it is the combination of innovation from the labs of Buchwald and Spencer that has led to this unique opportunity to commercialize an off-the-shelf catalysis screening platform. I'm very pleased today to introduce to all of you Catalysis high-throughput screening kits that are commercially available for the first time exclusively from Aldridge. So to develop these kits, Aldridge partnered with ChemSource and their roundtable of over 25 medicinal chemists from some of the largest global pharmaceutical companies that teamed up with the University of Pennsylvania's High-Throughput Screening Center to design, test, and validate the first screening kit, the Buchwald Hartwig amination. As you can see here, the kit is composed of 12 Buchwald pre-catalysts in a 12x2 array, and these catalysts are pre-weighed into microvials with tiny stir bars, and with each kit you receive 4 individually packed sets of these catalysts that are weighed, dosed, capped, and packed under nitrogen for long-term storage in your lab. You'll also receive 2 of our SureSeal solvents, dioxane and DMAC, which are ampulized for ease of use. The kit comes with 2 bases, a sodium terbutoxide solution, also SureSealed and ampulized, along with a pre-weighed, finely ground dry cesium carbonate, and substrate vials and perfectly fitting stir bars are also included to ensure adequate mixing prior to dosing. Knowing many of you have analytical HPL systems, we've also included an internal standard to allow quick analysis of the 24 reaction screen. And as I mentioned, the kits come in a pack of 4 catalyst sets and contains adequate solvents and bases to allow a modular design, in that you can choose to run up to 4 different screens with the contents of the kit, or you can choose to run 4 identical sets or any combination you may need. Now, the Buchwald Hartwig is just the first kit to become available, with many others currently in development. The Suzuki Miura reaction will be available soon, and we also have custom kit options available. All kits are designed to be used with our custom labware. The metal reaction block can be heated to elevated temperatures while ensuring a tight seal to minimize solvent loss and cross-contamination between reaction wells. The torque screwdriver provides this accurate seal every time and reduces stripping and over-tightening of screws. The small screwdriver allows you to remove the torque screws at the completion of your reaction. Of course, this platform works fantastic in a glove box, but in case you don't have one or you don't like using the one that you have, we're pleased to introduce the benchtop inertian box inspired by the ones at Merck that simply attaches to your inert gas line, allowing you to set up your screen quickly and efficiently in your hood under an atmosphere of nitrogen or argon. Now, while you're all very adept at setting up chemical reactions, there's a bit to learn the first time you attempt this new approach. So we have provided a library of comprehensive online tools. The first is a user setup video that's intended to be used alongside the detailed step-by-step user guides. And embedded in each of your user guides is a downloadable reaction calculator. This acts much like your electronic notebook, where you simply enter in the molecular weight of your substrates, and it produces a recipe for your unique substrate mixture. The print function allows you to take this recipe to your balance for weighing, and also allows you to save it as a PDF to append to your Ellen, as it contains all experimental details. The calculator also has a quick setup guide, as once you run a screen or 2, you will be a pro, and you only need basic reminders while setting up. If you want to learn more, I encourage you to check out our short YouTube video that provides a demo of setup and a website for full details. You can, of course, also just Google Catalysis to find the links to the products on the Sigma-Aldrich website. And if you have any questions, you can send a note to catalysis@sial.com, and this email comes direct to me. And I'm looking forward to hearing from you and answering any questions you may have. Shortly after this, you'll receive an email from us with an archive of this webinar and a note asking if we can send you periodic updates. If you're interested in catalysis in general, and more specifically in high throughput reaction screening, I encourage you to sign up to this list, as very soon we will have a comprehensive cross-coupling guide from a recently minted Buchwald PhD student, Dr. Nick Bruno. And this guide will provide the first attempt for your reaction, and if you're not satisfied with those results, the kit becomes the next logical step. And along with this guide, we'll also send some link to some pertinent papers, some of the ones from Spencer and his group, and other resources you might be interested in, including updates on the launch of new kits. So with that, I want to thank Professor Buchwald and Dr. Spencer Dreher for setting the stage for the launch of what I believe will be a great leap forward in the way synthetic chemists approach catalysis troubleshooting in their workflows. I also want to thank all of you for taking time out of your busy schedules to join us today. So we now have time for a few questions, so I'm going to pass this back for the Q&A to begin.
Okay, fantastic. Thank you for that, Sarah. So let's wrap things up with our question and answer session. If you do have any questions, please do submit them into the question and answer box, and we'll get those put to our speakers for you. If your questions do not get answered today, don't worry. We will be getting back to you with responses to those questions. So we've already received a number of questions, so we're going to do our best to go through as many of these questions as possible. So the first question that I've got here is actually for Professor Buchwald, and is, what do you see as the difference in difficulty between PD catalyzed CN and CC couplings?
Okay, I think, does Sarah have to, okay. So I think that the major difference is that the carbon nucleophiles, let's say either Negishi or Suzuki Miura, are relatively similar. Of course, there are differences in terms of stability and nucleophilicity, but when you look at CN coupling, it's really a much more complicated problem because of the differences in pKa's and binding abilities between, for example, amides, nitrogen heterocycles, aliphatic amines, aromatic amines, and also the fact that these can bind multiple times and play havoc by knocking off the ligands from the palladium center. So it's much harder, as Spencer said. Everybody wants the magic bullet, but if one is really lucky, you have a magic bullet that works for a particular substrate class, and even that is still quite challenging when one gets to real life substrates.
Okay, great, fantastic. So the second question that I've got come in is actually for Spencer. What are your thoughts on including additives in screens that do not have any obvious role in the reaction mechanism?
Yeah, I think we've used a lot of additive screening, especially in process chemistry at Merck. I think that you can see a lot of these sort of additive effects as being grease in the wheels on reactions where you might be helping to shuttle electrons or block binding groups, activate, via, sort of well-known mechanisms. But the problem is you're not going to impact probably medicinal chemistry in that way as much because you're not going to be taking an irrational approach when your material is scarce. So, generally speaking, you're gonna want to apply very rational problem solving. If you know a molecule is of extreme value and you're going to work on it for a long time till you get there, certainly is something to consider. But yeah, so I think it has its place, additive screening.
Okay, great. So another question for Stephen. Which of these reactions do you think would be suitable for undergraduate labs?
Well, I can just say the one that I know has been used is the one from Harvard that was shown on the slide for their chemistry 135, I believe. And actually, one of my current graduate students said he did it, so maybe that's why he decided, and it must have worked, so he decided to join my group. But that one works well, and with the pre-catalyst, you can do a variety of different coupling reactions quite simply. So it just depends on what you want to show. I mean, I would say, for example, the coupling of an aniline with an aryl bromide is one that would exemplify a lot of things, and has a very, very high chance of working unless one picks the absolute worst substrate combination. So I think that would work well. I mean, in the Harvard case, they both make the pre-catalyst and they utilize it for what was, until our publication, almost an unknown transformation, that is the Suzuki-Miura coupling of 2,6-difluorophenylboronic acid because of its instability.
Can I add?
Yeah, of course.
One sentence. At the University of Pennsylvania, when Jason Schmink was a postdoc, he's a professor at Bryn Mawr now, they ran a lab class using a kit, 24 reaction screen, just like Sarah is presenting here. So I think that's something that's interesting as well, where they did a Suzuki kit in their lab class at Penn.
Okay, so I've got another question coming in for you, Spencer. I'm very curious to know what role design of experiments algorithms play in your approach. Do you just sample the space, or do you have machine learning-based algorithms to determine the best catalyst, ligand, solvent, etc.?
Yes. That's absolutely the goal. In my opinion, all of this high-throughput chemistry is sort of part one of the solution. Part two is exactly what you said, computer-based learning and big data. And I think we're definitely working in that direction. I will say, in all honesty, we don't do it very much now. But it's something that we really have to start taking seriously if you want to, improve the probability of solving these types of problems in a sort of a business responsible time frame. So, yep. And just also first principles mechanism work, trying to understand why it works, why it doesn't work. So, all of that is critically important. I think this is a first step, though, is a really large step forward to try to solve these problems.
Okay, fantastic. So I've got a question just come in for Sarah, actually. Did any of the kits that worked in the immersion box not work on the benchtop under normal atmosphere?
We've done some studies on that internally, and I know Spencer actually has probably a lot more experience with this through the various catalysis groups at Merck. What we do see is that these are fairly robust catalysts, so typically in medicinal chemistry, people will just kind of chuck everything in and sparge their solvent very quickly, and they have some pretty good success. We do find with some more complicated substrates, though, that you really do need an inert atmosphere, and so the inertion box is a great place to perform those reactions, and it's always just a best practice to especially the first time you're running something, to give your reaction the best chance of success. So I always recommend something like the inertion box or a glove box if you have one. I don't know, Spencer, if you have any comments on that further?
Sure, yeah. I mean, the honest truth is a lot of times we are dealing with extremely difficult reactions where we might be happy to get one catalytic turnover. And if you're, whatever oxygen you have in your headspace, you're going to eat it up with a little bit of palladium. You're just going to be reducing the small amount of material you might have gotten. In medicinal chemistry, a 10% yield sometimes can carry you forward. You might miss some of that stuff. But we also screen oftentimes a 10 or 20% catalyst, and again, a little bit of oxygen in the headspace isn't going to be a killer. So we default to running in the glove box typically, just to make sure we don't miss any sort of low-level reactivity in our systems.
But can I don't know if you can hear me or not. Yeah, okay. So I would say, this is Steve Buchwald, I would say that, we actually use when we're running the reactions, I try to push my coworkers to use the lowest tech methods that they can. And so we will use disposable test tubes with repierceable septa, and we would use oftentimes sure seal solvents where we don't do any additional freeze, plump, thaw, degassing. We don't do any reactions in the glove box. We weigh everything out in the air. The only thing we use the glove box for is to save bulk quantities of base like sodium butaoxide or cesium carbonate, which in a Cambridge summer would melt with the water. And so, but the students will bring out a couple of grams, leave them in a desiccator for a couple of weeks to a month, and again, weigh everything out in the air, then inert it. Certainly we run the reactions under an inert atmosphere, but we're not super hyper scrupulous. You know, we could probably get higher yields otherwise, but in fact, what we're trying to do is to make technology transfer easier for the users.
Okay, that's fantastic. And thank you for all of those insightful responses to the questions that we had coming in. Like I said, if you did have a question that you didn't get answered in today's session, don't worry too much because we will be having the responses sent back to you at a later date. So that concludes today's webinar, in fact. So thank you for joining us today for WTG's webinar. It's been fantastic that you could all take the time out. And a big thank you to Sigma Aldrich and, of course, our speakers, Professor Stephen Buchwald, Dr. Spencer Dreher, and Dr. Sarah Treese. So one final thanks to our sponsor, Sigma Aldrich. Thank you and have a great day.